So we have done the stiffness metrics for a one-dimensional bar element. Next we move on to the force terms. Let us first consider the force term due to body force. This is in continuation with the previous derivation, so I'll continue with the numbering of the equations. These terms we had used in the derivation for stiffness metrics. Now substituting all these values in equation 6, we will get and this can be written as solving the integral and substituting the value of n1 and n2 shape functions. Now when we solve for this one, we will get square root by 4 minus 1 to plus 1. When we substitute the upper and the lower limits, we will get 1 here. Similarly, when we solve for this integral, we get 1. So we get Qt into Q transpose into the body force F into area of the bar element, length divided by 2, and the vector 1 1, okay, which is of the form Q transpose into F, where F is the body force vector given by A L F by 2 1 1. This we will call equation 7. Now this is as simple as this. This is not very difficult to understand because say we'll call this F E. Say we have a bar element like this which has a force, body force acting over the entire volume of the body. So it is but obvious that if you want to calculate the force due to body force or the reaction due to the body force at points 1 and 2, it will be, we're given a body force, the body force is always given by, say if we have density for example, so we can say the density, which will have units of force per volume, okay, multiplied by the cross-sectional area multiplied by the length. This will give us the force term, right? That this is the entire force. Now we want it at 2 nodes, so we will divide this by 2. So this is what it stands for. A, L, F. F is the body force, which could be the density. divided by 2 and 1 and 1. So this is at node 1 and this is for node 2. So it is equally distributed to 2 nodes of the bar element. So this was about the body force term. Next, let us go to traction force, and the traction force is given by, similarly the same way, it will be TE LE by 2. This is LE 1 and 1. You can derive it in the same way that the body force term was derived. So the element matrices KE, FE, TE are obtained after the element connectivity is established and the potential energy is written as pi equals to half Q transpose KE into Q. So we know here KE is the global stiffness matrix. This concept of local stiffness matrix and global stiffness matrix will be clear once we solve examples based on this. Okay. F is the global load vector, and U or Q is the global, capital Q is the global displacement vector. Now to solve problems, we use the equation K equals to F into Q, that is stiffness equals to the force into the displacement. This will be required when we are solving one-dimensional problems. Thank you.